Hello, and welcome back to another episode of the natural number game using Lean 4. Today we'll be picking up where we left off in the inequality world. Starting with level 6, less than or equal to anti-symmetric. Theorem less than or equal to anti-symmetric is defined as A and B are natural numbers. And we have a hypothesis AB such that A is less than or equal to B. And we have a hypothesis HBA, which says that B is less than or equal to A. We want to prove that A equals B. Okay, let me also just move these to this line. This kind of reminds me of like how you prove two sets are equal to each other in set theory. You show that one is included in the other, and the other is included in the one. That means that they're the same. Okay, let's think about how we can prove this. So we have A equals B plus C, B equals A plus C. Maybe we can do some rewriting. I think that's probably the way to do it. Let's do the cases HAB with vertical bar, intro. I'll do, C, HAB. Nice, we have C, and then we can also do cases HBA with vertical bar intro. I'll call this C prime, HBA, and then we want to show that A equals B here. B equals A plus C, A equals B plus C prime. What happens if I try to call this C? Will this have like a name collision or something? And there's like two C's. Yeah, I don't want that. C prime. Okay. Well, I know in both these cases C and C prime is 0, but can we prove that? I guess we could maybe do like if we rewrite B as A plus C, then we do A equals A plus C prime, and these are all natural numbers, and then so this will imply that C equals 0 and C prime equals 0. But can we get the fact that C prime equals 0? What happens if I do something like, what did the exist things do from last time again? Exists. Oh, no, that's if we have it in our proof state. A plus C. A equals B. A equals B plus C prime. Yeah, I could like rewrite into each of them, but that doesn't really help. See if there's any hints. In an advanced addition world, you prove that equals 0 of add right implies equals. Okay. So what we can do is we have from our advanced, probably want to also import mynat.advanced addition world. We have this tactic eq 0. And what does this say? This one says rewrite. This about this says that for all a and b, a plus b equals 0 implies b equals 0. So we'll save this one in the back burner. So I'm just going to have a comment that says that. I guess we could, let's see, rewrite HAB. Oh. Okay, that works. Okay, so we can define new hypothesis, but I want to write this at HBA. Okay, and now we could do have H defined equals 0 of add left right on HBA. Oh, okay, we want to do add associative. Add associative. Nice. Okay. HBA. Okay, so we want to also put in A C plus C prime. Do we also just do underscores? Why did you not work? Oh, it's because backwards. How do we flip inequality? Can we flip inequality? Must be equality dot equal or reflexive. What is that? Let's see. So associative. Is it capital E, capital Q? No, just this dot symmetric, maybe? What does this say? Okay, I think equality dot symmetric could be equality dot symmetric of HPA. Nice. Okay. So this gets us yeah. Okay. So equality dot symmetric. Let's flip this, and now we have C plus C prime equals 0. You want okay. Let's just call this H1. Okay. Well, we can do it again. Have H2. And now let's apply this to H1. We don't even need symmetrical. We should apply to H1. Does this not get us? Yeah, C2 equals 0. Why is this so red? O equals C. Never mind. Is there like an equals 0? Like 0 equals 0? So here we have C plus C prime equals 0. We want to have either C equals 0 or C prime equals 0. Let's check in the advanced addition world. Maybe there's something there that can help us. Oh, add left equals 0. We want to use that. Okay, that says that if a plus b equals 0, then plus b equals 0. Okay. We can use that. H2. Nice. And then rewrite H1 at H2. Oops, or H2 at H1. 2 at H1. Rewrite H2. Add 0. Rewrite H2 at H1. Rewrite add 0 at H1. Huh? Oh, that's annoying because we have plus 0. Let's see. 0. Of that. Okay. 0 equals numeral. Might need this in reverse. Sure. Guess I'll move you here then. And then we can like, it's nice to be working with the other 0, so I'm just gonna go backwards. Okay, and now we have C2 equals 0, and then finally we can rewrite at HAB H1 and add 0. Okay, in that case we don't want to change, we don't want to go backwards. Add 0. And then finally we also want to rewrite equal dot symmetric. No, you have to apply that. 0 exact equal dot symmetric of HAB. Ta-da! We have our proof such that these two are equal. And this stuff we added in advanced addition world came very much into handy here because we were able to use equals 0 of add right equals self and add left 0. Okay. Recap about something I learned is with this have expression, the have h equals e adds the hypothesis h of t if e is of type t. Okay, so can I just do like have h3 equals h2? And then maybe I could do, if I want to go backwards, I can do, this gets me hypothesis. And h3 is that in reverse. Okay, cool. Yeah, so this have is very useful for introducing new hypotheses we can use. And then, so things like this, something implies something else, are very useful as theorems or lemmas to apply with have with the current things we have. Nice. Okay, let's move on. That was a cool level. Less than or equal to 0. Okay, so let's do this. For all naturals a, if a is less than or equal to 0, then a equals 0. Okay. Theorem. Less than or equal to 0. A is a natural number. H implies that a is less than or equal to 0. We want to prove a equals 0. And how will we do that? We will do that with going to tactic mode and doing cases HAB with intro B, oops, H. Okay, A equals 0. Then we can have H prime be defined as add right equal 0. Well, we can even just use like right. Okay, let's do things. A plus B equals 0. No, we do want to add right. Okay, so this is saying A plus B equals 0. Okay. Oh, and then add left is saying B equals 0. We want to prove that A equals 0, so we go back to add right, and then we want to do equal dot symmetric of that. No, I guess we do equal dot symmetric of H. Equal dot symmetric of H. And then exact H prime. Or we can skip the middle man and then just do this. So wait, do we even need this B? Can we just do this? No, because it's different H. Okay. We don't need this B. It's a pretty cool proof. I wonder how we could do it in one line, because I feel like it's like close to be able to be done in one line. But we need this other hypothesis. What does this hypothesis say again? 0 equals A plus something. This A is less than or equal to 0, so that means that 0 equals A plus something. Okay, that was a lot easier than the last one. Let's move on to level 9, less than or equal to total. Theorem, less than equal to total. A, B are natural numbers. And we have, okay, A, and our thing we want to prove is A is less than or equal to B, or B is less than or equal to A. Okay, so we're doing something with or. And let me look at my advanced proposition world to see how we dealt with stuff with or. Okay, so our goal is an or. Okay, so with ands we did a constructor and exact. Okay, but we want to do our goal is an or. So we have or dot right injection, and then we also have or dot elimination proof by cases. Okay, so we're gonna have some or elim stuff going on. I'm just gonna copy this over. Oh wait, this is proof by cases of an or. So this we actually need to provide an or statement. So this might not be exactly what we want to do. So you provide an or statement. Yeah, so we can just do or dot one of these. So exact or dot. Yeah, so we can get A or B from A or B from B. Okay. Then can we get anything? Can we like extract anything from here? Can we like intro? No. Okay. I'm gonna think a bit about this. Okay, after thinking about this a little bit, if I write like if I do cases on A, I split like two cases, like okay, A is 0 and A is successor like of some things. So that's that with cases on A, and I can do something similar with cases on B. And so we'll either have a few different cases. So if I do cases on A and cases on B, we'll have A is 0, B is 0. Okay, that we just say they're equal to each other, and that's, or one is less than or equal to the other, and that's fine, because 0 is less than or equal to 0. If one's 0 and the other's not 0, that's fine, because one will just be less than or equal to these other. But then if they're both successor of something else, of them like successor of A prime, successor of B prime, they're kind of back where we started. But being back where we started is fine because that kind of sounds like induction. Maybe we do some sort of like induction. Induction A with induction A 0. Successor A prime each. How do I do this again? Induction. Oh, induction with. Okay. So this one, and then in this case, we'll probably want to do another induction. Induction B with 0, that should be easy. Successor B prime H. H prime. Okay, so we have H and H prime. And we have goal A. I'm not too sure what we need to do for this case. This one also seems kind of hard, but let's see if we can do the other ones at least for some confidence. Okay, so if this one's 0, well, we have theorem less than or equal to 0. Maybe that kind of in reverse, so we want 0 less than or equal to. For all A less than N, 0 is less than or equal to N. Okay, so have goal B. And then can I do like or exact or dot in right goal? O and L. Okay. So we just do this. And that takes care of the zero case. And we do something similar here. Exact zero less than or equal to successor A prime. Okay, so that takes care of those two cases. And that's fine. And now we have the thing that I thought would be harder. Okay, I can't even. I'm just gonna call this A, B because it's kind of hard to see all the primes. I can call this A. That's fine. Okay, H prime is A less than B, A less than or equal to B, or B less than or equal to A, implies successor of A less than or equal to B, or successor of B, or B less than or equal to successor of A. Okay, it's like, okay, and then H is A less than or equal to successor of B, or successor of B less than or equal to A. And so we kind of have like either successor applied to A or successor applied to, okay. But we need to have, okay, so we can maybe use H prime. So I don't think we can use H prime because I don't think we can prove A less than or equal to B or B less than or equal to A. H, on the other hand, H seems kind of promising. Because H seems promising because, okay, but why do we here we have, okay, why do we get this nice H from here, but from here we get this like uglier H prime inducting on B versus inducting on A. I'm not sure, not important. I think we can probably use, okay, so we have an OR statement. We can use OR.elim. Okay, exact OR.elim H this. Okay, so this is saying, because H is an OR statement. Okay, so function input to, sorry. And here input is this, okay. Function input to, sorry. Let's give input another a better name. A less than or equal to successor of B. This is successor of B less than or equal to A. Okay, so in this case, we have A is less than or equal to successor of B. Okay. So can we say anything? So A less than or equal to successor of B. Can we put a successor around A? What do we have with successors and less than or equal to? Less than or equal to successor. Okay, A less than or equal to B implies that A is less than or equal to successor of B. Okay, so we could add a successor always on the right side of less than or equals to. That makes sense. Okay, so then we could, oh, wait. So we can always add a successor on the other side. And then if we have two successors, can we get rid of one? Do we have a thing for that? No, maybe I can add that if needed. Okay, so our goal. Goal here is to have either successor. Okay, so we have our assumption that A is less than or equal to successor of B. Okay. I feel like we're kind of what I want to do is I want to like add one to A and then be like, okay, either one thing is true, either it's now bigger than successor B or it's smaller, but that kind of is a roundabout way of getting back to where we came from. Hello, so I tried less than or equal to total, spent about half an hour, recorded my thoughts, my process, got stuck, got confused, didn't really finish it or figure out how to solve it. So I'm gonna stop the video right here. I'm gonna try to solve this one on my own with a piece of pen and paper, and then start this fresh the next day or with the next video. Thanks so much for watching, and catch me next time where I tackle less than or equal to total. Definitely the hardest problem I've had to face yet.